Hello, and welcome to today's OSA Technical Group webinar, Chip-Scale Terahertz Frequency Combs and Multiheterodyne Spectroscopy. My name is Hannah Walter, and I am the Technical Community Manager here at the Optical Society. I'd like to thank you all for joining us for this webinar, which was organized by our Laser Systems Technical Group. OSA offers over 40 different technical groups to bring together the communities around selected subfields of optics and photonics. It is through the efforts of the OSA members who volunteer to lead these groups that we're able to offer unique and engaging events tailored to your interests, such as today's webinar. You can learn more about all of our technical groups and find out about upcoming events by visiting osa.org/technicalgroups or by connecting with us on LinkedIn or Facebook at any time. Before we begin today, I wanted to note that we will be addressing your questions at the end of the presentation. If you would like to ask our presenter a question, just click on the blue chat button at the bottom left of your screen. You will then be able to submit your question in the sidebar that pops out. At the end of the webinar, we hope you will take a minute to provide us with your feedback by completing a quick 5-question survey. You also will be able to download a PDF copy of today's presentation directly from that survey page. A copy of the slides and a link to today's recording will also be emailed to you following the conclusion of this webinar. Now it is my pleasure to welcome Shamsul Arifin, who serves as Vice Chair of the Laser Systems Technical Group. Shamsul will tell you a bit more about the technical group, and he will introduce you to today's presenter. Shamsul, the floor is all yours.
Thank you very much, Anna. My name is Shamsul Arifin. I'm from the Electrical and Computing Engineering Department at the University of California, Santa Barbara. I have been serving as a Vice Co-Chair in OSA Laser Systems Technical Group. In fact, today's webinar is being brought to you by the Laser System Technical Group, as Hannah already said. This technical group is currently chaired by Dr. Fatima Tur, Assistant Professor in the Electrical and Computer Engineering Department at the University of Iowa. And yeah, you could find more information about our technical group on the OSA website, as also Hannah said. On this slide, as you can see, that a large leadership technical committee with a lot of active members. And yeah, please feel free to contact myself or any one of us in order to know more about our group. And needless to say, we welcome participation from the community. And yeah, we are part of Photonics and Optoelectronics Division among several ones in the OSA. This group especially addresses technical issues concerning novel laser system development for a broad range of scientific and real-life applications. This group is also sometimes referred to as PL, as you can see on the slide, where P stands for photonics and L stands for laser. One of the activities our technical group is currently involved into is arranging the webinars at a regular basis on several topics related to light sources covering the spectral range from the UV all the way up to the terahertz, and today's webinar is certainly the reflection of that. As a matter of fact, our technical group is currently involved into a diverse range of activities, including arranging a feature issue on several emerging topics related to lasers and the associated systems, as well as arranging relevant events in several OSA and non-OSA based conferences. On the next, you can see that our LinkedIn and Facebook pages, which are great places to look at in order to get updated about upcoming events, including the ones as I already told you. And sometimes also relevant job openings are posted, so please keep your eyes in order to get updated. And I would strongly encourage everyone to join our LinkedIn and Facebook pages. And finally, on today's webinar, we are very delighted to have Dr. David Burghoff from MIT as a speaker, and he will be giving his talk on chip-scale terahertz frequency combs and multiheterodyne spectroscopy. Dr. Burghoff is a research scientist in the research lab of electronics at MIT. He received his bachelor's in electrical engineering from University of Illinois at Urbana-Champaign, his master's from MIT, and PhD in electrical engineering from MIT. So let's get it started. Dr. Burghoff, now the floor is all yours.
Okay, great. Thanks so much for the introduction, and thank you for inviting me. So the title of my talk, which you probably know, is Chip-Scale Terahertz Frequency Combs and Multiheterodyne Spectroscopy. I'm going to be discussing our work at MIT on the subject of terahertz quantum cascade laser frequency combs mainly. And so let me see if I can get the webinar. Okay, there we go. So the main motivation for this work is to do broadband chip-scale spectroscopy using compact sources. So many molecules at long wavelengths have distinctive spectral features due to their structure, especially in the gas phase, but also even the solid phase has distinctive lines. So on the left here is shown the absorption features of low-pressure methanol. On the right is the absorption spectra of several explosives. And although most of the work I'm going to be discussing today is done in the terahertz range, a lot of it also many of the same principles also apply to the mid-infrared range. So this is part of I have to acknowledge the sponsor, so this is part of the DARPA SCOUT program. SCOUT stands for Spectral Combs from UV to Terahertz. And the basic problem that we're trying to solve with this program is that the highest sensitivity spectroscopy systems tend to be large and have moving parts. So for a common example, here is an FTIR. An FTIR, its size essentially comes from the fact that it has a moving delay element in order to have maximal resolution. And in most of these spectroscopic systems, it's that spectral selectivity mechanism that actually increases the size of the system. So semiconductor laser frequency combs have the ability to perform high SNR spectroscopy without moving parts. And in this, I'll be talking mainly about, of course, about terahertz quantum cascade lasers, but this applies to other systems as well. For example, microresonator frequency combs or on-chip mode-lock lasers. And it's because of a technique that's called dual comb spectroscopy, which I'll explain later. But how it works is that it allows you to encode optical spectra into electrical spectra. So instead of looking at a spectrometer for your output, you're looking at an RF spectrometer. And I'll explain how that works later on. So just to give you a brief preview, with terahertz dual comb spectroscopy, you can perform broadband spectroscopy using chip-scale components with no extra active elements aside from your lasers and your detector. This is showing a silicon Schottky diode. And what you can do is you can, if you shine these devices onto this detector, then you measure an RF spectrum that looks something like this. And each of these lines essentially represents a pair of optical comb lines. So I've divided the talk really into three parts for the varying backgrounds of the audience. The first part is a very quick primer on the basics of a quantum cascade laser. The second part is on comb formation in quantum cascade lasers. And the third part is on terahertz dual comb spectroscopy based on quantum cascade lasers. So let's get into the first part, which is just to tell you a bit about QCLs. And what is a QCL? A QCL is a semiconductor laser that is essentially a large series of quantum wells and barriers grown on top of each other, which allow you to create artificial atoms. And by passing a current through your device and processing it into a waveguide geometry, you can get laser gain, which will allow you to have an optical source. And typically the structure of a QCL looks something like this. So it is a unipolar laser. What happens is electrons are injected from one side and they flow through the structure and flow out the other side. And what's nice about this is because you can control the spacing of your energy levels, you can choose your lasing wavelength by design and not by nature. And the reason it's called a quantum cascade laser is because one electron cascades down n identical modules and generates n photons. So what's most relevant for this talk is I'm going to be specifically focusing on terahertz QCLs. These tend to be grown in gallium arsenide algas. And for this system, in order to have a high-performance terahertz waveguide, we typically sandwich the gain medium in between two gold layers. So it's very similar in some ways to a microstrip transmission line. which has very low losses for this wavelength and allows you to fully confine the mode to within the gain medium. And of course, this is a plot that people want to show in the terahertz range. And what it's showing is it's showing the roll-off of power versus frequency for various types of sources. So electronic sources, they have difficulty going above 1 terahertz, whereas traditional semiconductor lasers have difficulty going below 10 terahertz. And terahertz QCLs allow you to sort of fill this gap, although you do need to be aided by cryogenic cooling. And what's also notable here is that the large power levels that are obtainable with these sources. So you can actually have watt-level intracavity power, and if you combine this with the large inter-subband nonlinearity, then this allows you to do devices that rely on nonlinear effects. So that's mostly what's relevant for this talk. So now I'm going to get on to comb formation in terahertz quantum cascade lasers. So what is a frequency comb? If you don't know, it's a light source that consists of a large number of evenly spaced laser lines. So for example, there's really only 2 frequencies that describe this system. One is referred to as the offset frequency, and the other is the spacing between the lines, which is referred to as the repetition rate. And these frequency combs are sort of a big deal. The Nobel Prize, I believe in 2005, was awarded for the development of frequency combs, and most combs were developed early on based on pulsed mode-locked lasers, although comb formation has expanded in the last few years to a large number of different systems. So the reason these combs are useful for spectroscopy is that you can do this technique that I mentioned called dual comb spectroscopy, where basically how it works is you have 2 different combs that have slightly different spacings, and you just do square law detection. So if this is showing the optical spectrum on the left, and if your 2 sets of comb lines have separations delta F1 and delta F2, then what you can see is that as you move along the spectrum, the comb lines walk off from each other. And when you shine these onto a square law detector, then the beating between different lines is going to appear at different RF frequencies. So this pair will appear over here, this pair will appear over here, etc. And so if you have an absorption feature encoded into your optical spectrum, something like this, then that same absorption feature will show up on the electrical spectrum that you measure. And so effectively this becomes a mapping of your optical spectrum. And the other name for this technique is called multiheterodyne spectroscopy, because these are basically a series of heterodyne detections that are occurring. And the optical spectrum is encoded onto your electrical spectrum. And of course, this can have broadband capabilities. It's as broad as the bandwidth of your comb lines. And because if it's laser-based, then it can have high sensitivity. And what's really important to note is that this doesn't require any moving parts. So of course, you don't need an FTIR, you don't need a grating or anything along those lines to do spectroscopy. And because of that, you can imagine making very compact, potentially even chip-scale systems. So the only optical elements you really need, aside from your sources and your detector, is you need to have, of course, some beam steering mirrors and beam splitters in order to get into your sample. But a lot of that, depending on the system that you're trying to measure, can actually be done on chips. So if you were trying to measure something in a microfluidic channel, for example, or if you were trying to measure a gas species which is around your chip, then you could imagine actually doing this dual comb spectroscopy totally on chip. And as I'll get into later, the coherence requirements are actually not that severe for this sort of system. So you can imagine making the whole thing chip scale. So how do you get a quantum cascade laser to form a comb? Well, one nice feature of quantum cascade lasers is that they're intrinsically broadband devices. So because they're semiconductor lasers, they have a large amount of spatial and spectral hole burning. And this will actually give you a broad spectrum. And because the gain media, you can put more than one gain medium into a waveguide, and so you can actually basically mix these together. This is called a heterogeneous gain medium to get even broader spectra. So that's a technique which was very nicely done by, for example, the group of Jerome Faith. They demonstrated an octave spanning gain medium. This is really the first step that you need in order to have a frequency comb. But it's not the only thing you need, because in general, even though this looks like a comb, if you were able to zoom in on the lines, you would find that the lines are actually, in this case, not evenly spaced. So one way you can tell whether something is a comb or not is to do what's called a beat note measurement. And the way this works is if you have a light source which is multi-mode in the sense that it has many lines, but those lines are not spaced evenly, then when you shine them onto a detector, what's going to happen is you'll measure the beating at different frequencies. So for example, this pair of lines will create this beat note frequency, and a different pair of lines will create a different beat note frequency. And those frequencies won't be the same. So what that means is that this beat note that you measure in the RF domain will actually not be particularly narrow. It'll be quite broad, usually on the order of hundreds of megahertz or even gigahertz. So that is not proof that you have a comb. It's proof that you don't have a comb when that occurs, but it's the easiest way to rule it out. So it's actually kind of interesting. It's been known for a very long time that spontaneous comb formation can occur in QCLs and also in terahertz QCLs. Basically, it's been observed as far back as 2000. So what happens in that case is that your beat note will spontaneously narrow from this hundreds of megahertz state into tens of kilohertz. So this was observed, I believe, first by the Capasso group in 2000 in mid-infrared QCLs, where they saw this narrow kilohertz beat note along with this broadband spectrum and attributed it to pulse formation. But because there was no mid-infrared autocorrelation, that turned out to not be the case. And more recently, in 2012, Jacob Kurgan and Jerome Feist essentially identified the output as being more similar to a frequency-modulated source. So the idea is that basically the output is frequency-modulated in a periodic fashion, but which allows you to get a narrow beat note, but there's no pulse being formed. And then more recently, we showed that by introducing dispersion engineering into QCLs, you could form combs relatively controllably. And I would point out that these two sources are in the mid-infrared, and this one is in the terahertz. So how do you get a comb to spontaneously form? Well, I'm going to show you a toy model. It's not quite accurate, but it's useful for understanding. And the idea is that basically you start with an incoherent multi-mode laser. So as I said, QCLs are semiconductor lasers, so they are naturally broadband. But in general, the lines of these lasers are not evenly spaced. So if you have your cavity modes, they look something like this. So you can see that this spacing is different from this spacing, for example. But if you allow for there to be some sort of intercavity nonlinearity, especially a chi3 nonlinearity, then what you can have is you can have four-wave mixing, which allows your lines to synchronize. And what this will do is pull new lines into the comb. So let me demonstrate how that works. If you have, first of all, degenerate four-wave mixing, then those two green lines can actually be together to create this dotted blue line. And this dotted blue line is actually, as you'll notice, it's a little bit off resonance. It's a little bit off where the cavity wants to laze. But through a process called injection locking, where the injected light can actually capture the original oscillator, this line will actually get pulled over. So this is very similar to if you have two grandfather clocks and you put them in the same room. Eventually, they'll actually synchronize just due to very weak coupling between them. And this process actually continues. So you can actually think of non-degenerate four-wave mixing actually doing the same thing to pull in an additional line. And potentially it can pull in more lines and more lines and more lines until you end up with a nice coherent comb. So your incoherent multimode laser is now actually evenly spaced. So all the lines have a definite phase relation. And that spacing is not quite equal to the mode spacing, but it's fairly close. So why is spontaneous comb formation more difficult to observe in terahertz QCLs? Well, the reason, of course, is due to intracavity dispersion. So if you look at this picture of sideband injection locking, you can imagine that if the light that you're trying to inject is too far off the cavity resonance, what's going to happen is that your injection locking will not be able to pull over the original line, and your multimode laser will effectively stay as a multimode laser. And this is equivalent to saying that the group velocity dispersion is too high. So why does this matter in the terahertz range? Well, 3.5 materials are particularly dispersive in terahertz due to the Rastral band, which is a function of phonon absorption. Basically, in gallium arsenide, at 3.5 terahertz, the dispersion is typically on the order of 100,000 femtoseconds squared per millimeter, depending on how close you are to that Rastral band. So, of course, what we wanted to do is we wanted to borrow one of the techniques from ultrafast optics in order to take this into account and to compensate dispersion. And so what we did is we developed double chirp mirrors, which were integrated into the laser cavity. So this is a situation where the periodicity of the chirp mirror grows as you go towards the end of the cavity. And what that does is it allows you to have long wavelengths penetrate further into the cavity than short wavelengths, and that effectively compensates dispersion. And when you do that properly, then what you find is that your multimode spectrum, which is shown in blue, can actually become a nice coherent comb beat note, which is shown in red. So actually, this is something that a lot of groups in this area have been doing recently. I'm leaving some people out for sure, but there's a lot of different papers in this area. Various GVD compensation schemes, for example, based on GTIs and coupled cavities and hybrid waveguides, and so on and so forth. So this is a way that you can use to repeatedly make frequency combs. So just to show you some more results from this data, what you find is that your spectrum remains broad, while your beat note is in fact narrow, depending on the environment that your laser is in, whether you stabilize it or not. And the comb state is semi-confirmed, but to actually do to actually fully confirm that the comb is being formed, you have to go a bit further. You have to show that each of these lines is beating at the same beat note frequency. And to do that, you have to do a coherence measurement. I won't get into the details of what's necessarily being shown here, but what this is showing is it's a measurement of the first order coherence. So this is G1. And the first order coherence is basically a measure of how definite the phase relation is between every pair of lines. And the fact that these two curves in both cases agree with each other is basically an indicator that G is close to 1, which is that your comb is almost fully coherent. And more recently, there's been work done by the group of Jerome Feist to do a similar measurement, a different measurement that measures higher order correlations. So you may be wondering, what does the actual time domain output of these lasers look like if they're not mode locked? Well, it looks something like this. Again, you can do this coherence measurement in order to determine this. So this is showing the intensity versus time for one of these lasers, and this is showing the frequency versus time. And as you can see, the output is actually periodic with the period that's shown here. But the intensity is not a pulse, and it's not uniform. It's kind of a lumpy mess. It's hard to put a name onto this. The frequency versus time, you can see, is also fairly strongly modulated. In this case, it ends up looking something like a square wave because of the shape of the gain medium. But it's important to note that this occurs basically because of the dynamics of the QCL. So this is because the gain recovery time of a QCL is generally quite short, and it tends to preclude mode locking. And there's been a lot of theoretical work to confirm that this is in fact the case, which is mentioned below. So I'm going to skip this slide. The last point I wanted to mention is that quantum cascade laser combs, under certain conditions, can also act as detectors as well as lasers. The reason for this is that the current through a QCL is actually a function of stimulated emission in the laser. So if you look at this structure hard enough, you can see that if you were to actually apply light to this lasing transition, then electrons will move through the system faster and the current will increase. And so what that means is that you can actually use these as a type of detector. And that was something that we've done using an external DFB laser to characterize some of the properties of these lasers. And what you do is you shine your DFB laser into your comb and you measure the output of this on an RF spectrometer. So when you do that, if this is the spectrum of your comb and this is the spectrum of your DFB laser, what you find is that you can actually measure a pair of beat notes, heterodyne beat notes, between these two sources, and this is measured actually out of the laser bias. So the frequency of these two lines, so this is the beating of the red line with its left neighbor, and this is the beating of the red line with its right neighbor. They add up to the spacing of the comb, and if you tune the DFB, then they tune in opposite directions, which is what you expect. The sensitivity of the system is not great, but it's sufficient. It's roughly, you're limited by the shot noise of your QCL, which is because your QCL is biased to about amps worth of current, your NEP ends up being on the order of nanowatts per root hertz, which is similar to pyroelectric detection. So the strength of these signals, for your reference, is roughly on the order of 10 microwatts. So that's some of the features of QCL combs. And for the last and largest part of the talk, I'm going to be focusing on multiheterodyne spectroscopy based on these lasers. So how can you use them to perform dual comb spectroscopy, and what kind of results you can get from that? And just to give you a brief reminder, I already showed you this, but it's very important. So if you want to take one thing away from this, that's what I would take away. It's that you're using your electrical spectrum to encode your optical spectrum. So a pair of beat notes occurring for these two lines will show up at a different frequency for every pair, which allows you to map your spectral features. So to give you a brief reference, typically the repetition rates of these lasers are on the order of 10 gigahertz, and the spacing between these lasers, the repetition rates is on the order of 10 megahertz down to DC. So it's kind of actually interesting to note that the first dual comb spectroscopy was actually done at terahertz frequencies, specifically at lower terahertz frequencies, so around 200 gigahertz, by Dan Vanderweide and Fritz Keilmann. Most of the work in this area has been done in the near infrared with mode-locked lasers. So there was a recent review from NIST, which nicely explains most of the issues associated with this. And more recently, it's also been done with mid-infrared QCLs, and even more recently, interband cascade lasers. So again, we're of course focusing on the terahertz range, which has its own unique challenges. In particular, the issue of the detector is the detectors that you need to use in this case are relatively hard to come by. So basically what you need is a high sensitivity detector at terahertz frequencies, which is also able to respond quickly, to respond to within gigahertz speeds. So we've actually used two kinds of detectors. So one is it's called an HEB. It's a hot electron bolometer. It's a type of superconducting bolometer, which is of course cryogenically cooled. And the other that we use is a room temperature silicon Schottky mixer, which is effectively a kind of diode. So this is what the source, the pair of lasers looks like in our optical setup. They're lens coupled, so that's what these little shiny features are. And for this measurement, The comb spectra aren't particularly broad. They're about 300 gigahertz, which is helpful because the power consumption of these lasers is relatively low. So what does the dual comb spectrum of these lasers look like? Well, of course, it depends on what kind of detector you're using. So this is a signal which was measured on both an HEB and a Schottky mixer at the same time. So these are effectively different versions of the same signal. The signal on the hot electron bolometer is a bit stronger. It's in the order of 10 to 20 dB stronger, and that's because the HEB is a superconducting bolometer and is more sensitive, although the Schottky mixer has other advantages, particularly that it's not cooled and that it's relatively linear. So when we did this work, we did some initial spectroscopy based on an etalon. So this is effectively just a piece of 600 micron gallium arsenide, and when you which has very puro fringes, and when you plot the spectrum with the etalon and without the etalon on a log scale, it's sort of difficult to tell what's happening because the absorption isn't so strong. But if you plot on a linear scale, you can see that the agreement between the theory and the experiment is somewhat reasonable. The limiting factor here is mainly a combination of non-uniformity of the comb lines and also detector nonlinearity. So if you look at the comb lines that we're measuring, the intensity varies by about 30 dB, which means that if you have detector nonlinearity, a weak line can severely interfere with the signal that you measure of a weak line. So of course, you can actually use this to measure real samples as well, and this is something we've been working on more recently in collaboration with the group of Gerard Wysocki at Princeton, who have been doing a lot of this multiheterodyne spectroscopy based on QCLs. And this is a sample that they measured, which is high pressure, relatively high pressure ammonia. So this is at about 460 torr. What you can see is the absorption is, compared to the high trend data, agrees fairly well. If you assume that the presence of water, which is also in the optical system, just because this is the terahertz range and water absorption features are everywhere. You can also look at the spectrum of a more complicated sample, such as nitrogen dioxide. Again, this is relatively high pressure, so about 840 torr, and the agreement in this case is quite nice. And the residual for both cases is on the order of 10%, which is not quite state of the art as relative to mode lock lasers, but it's a starting point. And so you can do spectroscopy with these, and then for the last portion of this talk, I wanted to focus on a little bit more of a practical issue with these sorts of systems, which is the issue of phase noise in your lasers. So I keep showing this cartoon, and this cartoon is a nice descriptor for understanding dual comb spectroscopy, but it's not quite physically accurate because in real life, what happens is that you always have some phase noise on your lasers, and these are due to a number of things. So of course, there's fundamental noise due to spontaneous emission. There are environmental fluctuations. So if the temperature or the bias of your laser is fluctuating, or if there's optical feedback and the laser is moving around mechanically, which is also the case in these systems. And so what that does is it causes your nice delta functions to actually have some line width. And while you might think that this isn't necessarily an issue because compared to optical frequencies, this broadening is actually quite small, because this is a heterodyne measurement, when you move into the RF domain, what you can see is that the broadening is actually maintained. And because it's maintained, it becomes much more noticeable as this line width continues to increase, or as you integrate longer. And you can imagine that this could potentially be a problem Because what's going to happen is that if there's too much noise, or if you integrate for too long, then these lines are actually going to blur on top of each other. And when they blur on top of each other, then you're not going to be able to resolve the absorption features that you're measuring, or you're trying to measure. So I'll give you an example. So first I'm showing the effective phase noise in a low noise state. So this is a pair of lasers where we measure the dual comb signal over 100 microseconds, and the spacing between them is about 4 megahertz. And so in this case, you can actually, even though there's some noticeable broadening, it's relatively small, so it's only on the order of sub-megahertz, and so you can still resolve your comb lines. And you can actually potentially do spectroscopy with this. But if there are combs which are not as good, or if they're in a less stable environment, so you'll end up with something which is in a high noise state. And in this case, the two devices are still combs, and so the signal that you're measuring is actually, it is a multiheterodyne spectrum between the two combs, but you can't actually resolve any of the spectral features that you should see. So the spacing here should be about 35 megahertz, and you can't really see anything in this spectrum, which looks like an RF comb, which is spaced by 35 megahertz. So that's an issue. So you can ask yourself, okay, well, maybe if I integrate for less time, then I'll be able to see this. And you'd be right about that. So if you actually, instead of doing 100 microseconds, as was shown on the previous plot, if you do this over 1 microsecond, you can actually see the RF comb being formed. So you can see that there's an RF comb here. The problem is that this RF comb is very strongly fluctuating. So if you actually track the offset frequency of your RF comb, you find that it's doing something like this. And it's moving around by a fairly large distance, even over short time scales. And the magnitude of this fluctuation is roughly 3 times the repetition rate spacing. So this spacing from here to here, the fluctuation is roughly 3 times that. And that is essentially the reason why the spectrum that I previously showed is getting blurred. So when the lines blur by more than 1 times the repetition rate spacing, then the spectra cannot be easily interpreted. So what can you do about that? Well, there's been a lot of work done in the mode-locked laser community, particularly on these adaptive sampling approaches. And what these are is they are a series of schemes which allow you to actually correct for your dual comb signals after the signal has been acquired. So what you do is you record a reference channel alongside your dual comb signals. In this case, you're reading with a continuous wave laser. In this case, you're measuring with a bandpass filter, and then you record some extra reference channels. But we couldn't do this because we were operating at long wavelengths. In this regime, you're usually detector noise limited, so you don't have any optical power to spare. If you use a reference beam, then you'll have to ultimately sacrifice some of your signal-to-noise ratio. And if you have not too many detectors and lasers, then you also want to avoid adding extra components to your optical system. So the question is, can you do this totally digitally? And the answer is yes. And the idea to keep in mind is that if you have a perfect measurement, your RF spectrum will look something like this. And if you don't have a perfect measurement and they're blurred on top of each other, then it'll look something like this relatively flat curve here. And what you should notice is that when this happens, the phase noise is large, but it's actually still correlated. So really, if you want to think about it one way, the phase noise covariance is basically rank 2. So it can only fluctuate in one of 2 ways, which is for the offset to fluctuate or for the repetition rate to fluctuate. Any other fluctuations are a deviation from the comb state, which is not occurring. So you can actually extract this corruption digitally without using any optical components. So effectively, this is adaptive sampling without any extra optical elements, which is really nice. So the way you can do it, there's actually more than one way you can do it. There's a few ways that have been demonstrated recently. But the way we did it was we used extended Kalman filters to track these frequency fluctuations. And so what this is doing basically is doing a regularized fitting problem not quite in real time, but on a point-by-point basis. And so what you're doing is you're extracting out the instantaneous offset frequency and repetition rate as a function of time. So this is an example of what these curves might look like in one of these high noise states. You can see that there's strong fluctuations on both the offset frequency and the repetition rate. And if you look at the structure of your comb measurement, what you'll see is that the offset frequency corresponds to a phase factor, whereas the repetition rate corresponds to a time stretch. And so by reversing the phase factor and the time stretch, you can actually correct for these fluctuations. So what does that look like? Well, here is another case of a high noise multiheterodyne data. You can see again that there's no visible dual comb signal observable here. What you're going to do is you're going to multiply by the offset fluctuations, so that ends up being a convolution in frequency space. And so when you convolve these two together, what you find is that actually your offset fluctuations were responsible for most of your blurred spectra, and you find actually your blue spectrum has corrected quite nicely. You've recovered all of these dual comb lines, which were effectively buried in phase noise. And you can actually take this one step further and remove timing fluctuations. And when you do that, actually you find that some of the lines and the edges in particular have continued to correct even further. And that's basically because if you want to think of the repetition rate, it has an accordion type effect on your spectra. So the lines at the edges get blurred more than the lines at the center. And in fact, you can extract real signals that are also that weren't apparent in the original data. This is actually real data. It's not an artifact that has effectively been recovered from the noise floor. And the way that works is that if you want to think of it this way, your large signals here are acting as heterodyne references for your weak signals, which is what allows this to occur. And you can take this a step further. You can also cross-correct different spectroscopic channels. So we had 2 terahertz detectors, so we would record 2 signals at the same time from our 2 different detectors, and you can use the correction derived from just one of these to correct for both of them. So if you correct your data recorded on a Schottky mixer with itself, then of course the correction is going to look nice in that case. That's not so surprising. But actually what you can also find is that if you take the same correction and apply it to the other channel that is being measured, in this case the Hut electron bolometer, then the correction also works in this case, which is really showing that this is something that is real and is not just some sort of digital trickery. And actually, there's a lot of advantage of this sort of computational phase correction approach because it really removes the need for temperature stabilization and bias stabilization. It allows you to do pulse mode dual comb spectroscopy, which is something I'll touch on later. And actually, this approach that we did, we developed it for terahertz because of our unique limitations. But actually, more recently, it's been similar. Other computational approaches have been applied both to chip scale mode-locked lasers at the near infrared by the group of Jerome Ganest in Lovell, and also by interband cascade lasers by the group of Gerard Wysocki. And it's a very general approach, and you can actually correct many sorts of dual comb systems in this way. And so I mentioned pulse mode dual comb spectroscopy. I just want to show that very briefly. Basically, the reason for this is if you have a system where you are limited in power consumption, then perhaps you only want to turn your laser on for a very short period of time. So if you do that, then your multiheterodyne signal is going to look something like this. If your laser turns on at time t equals to 20 and turns off at time t equal to 140, you can see that, of course, your multiheterodyne signal has a square wave behavior. If you look at the spectrogram of this multiheterodyne signal, so this is frequency versus time, you find that there are really 2 regimes. So the first regime is this multimode regime that happens when the laser is initially turning on. In this case, you don't have a dual comb. You just have some incoherent structure. And then after the laser has been on for a while, it settles into a nice dual comb regime, which you can tell because you have this RF comb versus frequency. But what you can also see is that the laser is fairly strongly chirped due to laser heating. So you can see that each of these comb lines is shifting towards, in this case, lower frequencies, and also the amplitudes are changing somewhat. And that's basically because your laser is heating up during the duration of the electrical pulse. And you can, again, apply this same sort of signal processing to this data. And when you do that, you find that again, you can correct your spectra quite nicely. So the raw data is shown in blue, the corrected data is shown in red. The raw data, again, of course, you can't resolve any comb lines because the blurring is much more than one repetition rate spacing. But when you do the correction, it actually is recovered. And because this allows you to continuously correct for chirp and phase noise, then you can actually imagine doing systems where your power budget is very limited. So, for example, in the terahertz range, you need some amount of cooling in order to operate your laser. Not being able to operate in continuous wave mode is actually a large benefit. But even for mid-infrared QCLs, which do operate at room temperature, there are reasons where you would want to operate in pulse mode, especially because a typical QCL consumes on the order of 10 watts in continuous wave mode. So if you wanted to make some sort of portable sensor, that really wouldn't be a viable option. So this is really kind of, in our opinion, a step forward towards making these sorts of chip scale systems more viable. So in conclusion, I showed how using dispersion engineering, terahertz quantum cascade lasers could be used to operate in a comb regime. And I showed how you could actually do dual comb or multiheterodyne spectroscopy, both in pulse wave and continuous wave mode, in order to measure the spectra of some simple systems. And I also showed how you could use signal processing to reverse some of the phase and timing fluctuations that are inherent to many of these dual comb systems, making them much more practical. So with that, I guess I will end the webinar, and I again want to thank the organizers for putting this on, and now I'll take some of your questions. So thank you.
Thank you, David. We'll now open the webinar up to questions. As a reminder, you can submit a question for David by clicking on the blue chat button at the bottom left of your screen and then entering your question in the sidebar that's going to pop out. Our first question for you today is, what are the main limiting factors for spectroscopic applications?
Okay, so there are really, I would say there's a few. At this point, one feature that you may have noticed on the spectra that we measured is that there are very large gaps in the spectrum because the dual comb spectrum that you measure are only measured at discrete frequencies. And so actually, for practical systems, one thing that you need to do is you need to be able to tune those frequencies to cover the full FSR of your dual comb system and to basically have gapless coverage. So that's, in some ways it can be done with temperature and current, but it's a little bit ad hoc at this point. The second limiting factor, I guess, is of course you want better combs to start with. So you want more broadband sources. You want basically better spectral coverage because that allows you to declutter your spectra as well as possible. And then, of course, the third major limitation, which is actually a limitation on terahertz quantum cascade lasers, which is that they don't operate at room temperature. They require at least some cooling, at least TE cooling, but more often they are nitrogen cooled, which of course makes things a bit more difficult.
Okay. Our next question for you today is, what are the differences between quantum cascade laser frequency combs spectro in the terahertz range versus in near IR?
Okay, yes. So I think probably to my knowledge, there aren't actually QCL frequency combs in the near infrared because QCLs really only go up to the mid infrared. So I'll answer two questions. First, I'll answer what's the difference between QCLs in the terahertz versus the mid infrared. In the mid infrared, I would say typically mid-infrared QCLs in general have better performance than terahertz QCLs. So they can actually have higher powers even at room temperature, whereas terahertz QCLs cannot do that. The real advantage that terahertz has over the mid-infrared, I would say, is in terms of relative spectral coverage. So as I mentioned earlier, the group of Jerome Feist actually demonstrated an octave spanning gain medium at terahertz frequencies. And you can actually design this and you can actually make that. And so what that means is that you can cover, well, in case people don't know, octave spanning means that the lowest frequency in the comb is less than half the highest frequency of the comb. So what that means is that you basically have 50% spectral coverage. That would actually be much harder in the mid-infrared. So in the mid-infrared, you can have similar absolute coverage, and it'll be a few terahertz, but that few terahertz is fractionally much smaller. And then in the near-infrared, there aren't QCLs, but there are other types of frequency combs. Probably the two big main ones are mode-locked lasers, which I mentioned before are very well developed and have many lines, and you can do a lot with them. They tend to be larger. And there's also microresonators, frequency combs, which I didn't really discuss in this webinar, but it's a technology where you pump your laser with a CW laser you pump a microresonator with a CW laser, and you get a comb to form out of that. And dual comb spectroscopy was recently done with those as well. So yeah, I think I answered both versions of that question.
Great, thank you, David. Our next question for you today is, are there other types of frequency comb generators other than quantum cascade lasers that you see as promising for spectroscopy and/or other applications?
Is that specific to the terahertz range, I believe? Here, let me check. Okay. Yes. So I guess there's a few. Yes. Frequency combs. The technology that you're looking at is very dependent on wavelength. So in the terahertz range, actually, the most common broadband terahertz sources are actually terahertz time domain systems, and those are frequency combs. So those are in fact offset free frequency combs. So those are really nice for a lot of reasons. The one disadvantage they have relative to QCLs is that the average power is substantially lower usually. So with a QCL, you can integrate continuously, and because it's a laser, this is why you can have these very high signal to noise ratios, so 60 dB in very short integration times, so under 100 microseconds. Whereas in terahertz time domain systems, that tends to not be the case. Other frequency comb technologies, so in terms of chip scale applications, especially in the near infrared, the microresonators I mentioned earlier are very promising. You can actually get octave spanning spectra with those. And I believe that also some groups are working on some nice chip scale mode-locked lasers as well. And actually both of those technologies, I believe, can be extended even up to the UV, depending on the material system. So they're all fairly promising.
Our next question for you today asks, can these frequency combs be used for optical sampling?
So I'm not 100% clear. Maybe the author could actually do a follow-up question or a follow-up, I guess, comment. So optical sampling. Does that mean sampling an optical waveform at terahertz frequencies or at another frequency or something along those lines? Maybe they could follow up and clarify that. So if they're talking about if they're writing it, if they're talking about something like an IR domain, well, probably not. I'd have to. There might be a clever way that I can't immediately think about. You can do the opposite. So you can use an IR source to sample the output of one of these combs if you were to synchronize them together. I don't know if you could do it the opposite way, which is sampling an IR comb with a terahertz source. But what you would have to, if you wanted to sample a terahertz source with an IR laser, you could probably do it, and it would take. What you would want to do is you would synchronize the mode lock laser to the a multiple of the a subharmonic of the QCL repetition rate. So I believe Stefano Barbieri and Carlos Sartori have done something similar in their 2011 paper, and if they wanted to, I could give you a reference on that. But yeah, that's it.
Okay, great. And I think on that note, we are going to wrap up our question and answer session for today.
Okay.
Please remember, when you disconnect today, you will be prompted to complete a quick survey. You'll also be able to download today's slides from that screen. I would like to thank Dr. David Burghoff for his excellent presentation today, and also thank the Laser Systems Technical Group for organizing this webinar. On behalf of OSA, I would also like to thank all of you for joining us today. This concludes today's webinar, and you may now disconnect.